Good morning, everybody. Uh, Thank you for coming. There are lots of great choices for you to attend today, and thanks for coming for listening to me about introduction of gRPC. Um, Before I start, to make sure uh, what level of familiarity the audience has, I wanted to do a quick show of hands. How many of you have not heard of gRPC or have just heard of gRPC and are here to find out more about it? Fantastic. So that's the largest group. So great. So that I'll go to the next because I wanted to introduce. So in this talk, I'll be covering just basic beginner level information about what is gRPC, what do you get out of it. There are a few other talks today. There is another talk at 2:45 which talks about similar basic levels but how to apply gRPC for IoT applications. And then immediately after that, if you're running gRPC and if you want to scale gRPC application, want to learn about how to do load balancing with Kubernetes, then my teammate Jan would be talking at 11:45 in auditorium 15 about how to scale gRPC services and load balance them across Kubernetes. And then tomorrow at 4:30, Sree, my co-partner here, would be doing a deep dive. And that session is mostly if you are excited, you want to contribute, or you are contributing, or you're a power user and you want to dive into the stack below. That it'll cover that. So great. So let's get started. What is gRPC? Some acronym, 4-letter acronym. Well, it's a recursive definition. gRPC, remote procedure calls. So basically, it's a remote procedure call library. It's meant to be a high performance, standard based, open source framework. We've built it so that it's ubiquitous. It works in cloud native applications, in your data center, on your desktops, in your mobile phones, in your IoT devices. It's meant to run everywhere and gives you a same framework to develop your applications in that scenario. It's CNCF's RPC framework. It's been in CNCF for more than a year. Used to build cloud native apps, and it's been a next generation of a system called Stubby that we've been using at Google for over a decade. It's actively developed, production ready, and we just did a release. We've been doing 6 weekly releases, and its recent most release is 1.11. So what's a remote procedure call? You make a call to a remote service just like your procedure call. What does gRPC give you if you're developing an application? The green boxes here, consider a service you're running. You're running a C++ service, and then you have a Ruby client and a mobile client which are talking to this service. So the green boxes are what you get out of the box from gRPC, and then you develop your application logic around the gRPC. And we'll walk through an example, getting into details of what it does. So when I came last year at Berlin and I started talking, and the first question was, hey, you know that RPC, that's a 70s concept, old concept. There have been some failures like Corba, etc. What are you bringing new or this thing? So we've been using at Google RPCs for 10 plus years. We've built more than, we are actively running tens of thousands of services with tens of billions of RPCs per second. So this is not over a day or over time. This is tens of billions of RPCs per second. From those, we have learned a lot. And this being the next generation, we brought in all the use cases and things that we have learned into this. So we'll walk through a small example of to explain further what do you get, how do you build, and how do you go forward. So this is just outline, and we'll go through each of these steps in detail. But when you want to start building, you start defining, what am I building? What service am I building? You write a proto file, and I'll talk about that soon. And that Then you run a compiler, it generates a service and a stub for me. The service is what you use to build your service, stub is what you use to make a call. You're building your application around these, and then you're up and going within minutes with your distributed application. So I'll take a slight detour into protocol buffers. Protocol buffers and gRPC go hand in hand. They can be used without each other. People use protocol buffers without gRPC or stubby, and people use gRPC without protocol buffers. But together they make it very easy to use and give much more value add to people. It's been a lingua franca of Google for serializing and for RPCs and storage. Been using for a long time. It's a binary data representation, so it's compact. The structures in protobufs can be extended in forward-backward compatible way. You have to maintain certain conventions, and you can maintain your you can upgrade your services, or you can have support old clients and new clients simultaneously if you follow certain conventions. You define your ideal, and the code generator takes care of creating a custom library for you using that ideal, and then from your perspective it looks like you're programming to your application logic. So if you're developing, for example, a banking app, once you have defined and you have run, it looks as if you're writing add this money, withdraw money from ATM. Those type, you can think in terms of, you don't have to think. It takes away the distributed nature from your application. You don't have to think. When you scale, you will need to still think, but when you start, it gets you started quickly. And protocol buffers are strongly typed. That gives you that lets you create strict contracts between your clients and servers. Benefit of that is, if there are you can detect the errors at the compiler, this thing, rather than running it and stumbling into problems. You detect problems early, and it also allows efficient optimization, because what it lets you do is once you have written, then you can take that ideal and create a very compact binary representation from it. There are other integrations of gRPC with flat buffers and Microsoft Bond, and those are in open source if you want to see. The protocol buffers has a rich data type system, and you can see over here that there is a message with some enumerated types and then some repeated messages being specified as a list or array of messages. So now we know basic blocks we are going to use. Let's walk through an example. Let's say that I want to build an example called route guide, and it's a simple application. I'm traveling around my application is such that there are clients traveling around a route, and they are communicating with a service with some notes and information, etc. Or it could be between two friends traveling around two different routes and talking to each other. Doesn't need to be it can be a symmetric model too. So the first thing you need to think about is, what messages am I going to send, right? As you start building your application, you start thinking, what messages do I need to send? What type of service do I need to export? So, and you need to define your API. One of the anecdotal sayings at Google is, as you grow up in ladder in engineering at Google, the more senior you become, the more time you spend just writing protocol buffers, because that's one of the most important thing. If you design your API right, you're going to build a very long sustainable this thing. You have to think through all the corner cases, etc. So you want to think, come up with all the questions, do your design. So here I'm talking about a route guide. I'm thinking of messages. I say, oh, I need a point, location, latitude, longitude. I need a feature. Well, feature is probably name of a place at a point. And route note now is a note that I'm sending from a point along a route. And then I think about service. Well, I'm going to do a very simple service. I just need two things. Given a point, I need to know what is there a feature at this point and what the feature is, and then send some chat message to, say, Sree walking along his own route and explaining him what point I'm at and what feature I'm using, etc. So very basic service, but so as I said, you define your messages. Very simple. Those funny looking equal to 1, 2 tag IDs, those are the tag IDs that are required, and those are the ones that help you maintain forward and backward compatible nature of gRPCs if you follow certain convention. So the golden rule is never reuse a tag. If you don't ever reuse a tag, if you want to add a new, say after 6 months you add more functionality, add more tags. What that does is this format on the wire stays backward and forward compatible, and then it's up to your server logic when you want to handle, and you may decide to give an error, but you will be able to handle multiple versions simultaneously. So once you've defined your messages, these are the objects that you're going to send, then you need to start thinking about the definition service. gRPC allows two basic types of RPCs, unary and streaming. So unary is client sends a message and the server sends a response. Client streaming is client starts sending list of messages one after other, and once it's done, server sends a response. Server streaming is opposite of that. Server keeps on, you send a client sends a request and server keeps sending responses. And then bidirectional streaming is similar to asynchronous communication. I am talking to Sree and Sree is talking to me. I don't know when he's going to talk to me. He doesn't know when I'm going to talk to him. So clients and servers send multiple messages asynchronously to each other. So in this case, I'm going to add two RPCs, just one get feature, get given a point, returns a feature, and sends notes, this asynchronous communication. So this is what I do in the proto file, and then I run proto compiler. That's all you do. So I write my protocol buffer and my service definition, and I run a compiler, and I can generate code for any language that gRPC and protocol buffer support. So 10 plus languages, and get libraries to do that. And it creates idiomatic objects in those languages for these messages. It gives me getters and setters for all the types and all the message types. And it creates abstract interface for my service. So all I need to do is derive from this service class and create my service. So so what does it look? I ran this on C++ with a C++ option, and I got a service object and I got a stub object. The stub, I'll talk more about the stub a little bit. So what do I do from here? So I wrote my proto, I ran the compiler, I got this. Then I write my application code for service, creating a derived class from this class, and implement some handlers in that RPC class. So that service has a bunch of handlers that I can extend, and that builds my service. So you, from your perspective, you wrote your proto, and then you focused on how the application logic for your service works. Sorry. And then when you want to make a call, you use that stub, the word stub, or a client stub. You can think of it as a client. I use that stub and say get feature. That sends a message across to the on the wire to the service. And so if you think about it from an application developer's perspective, this is a much simpler model because you wrote your service contract, you defined it well. Please, whenever you write, make sure you take your time to design your APIs well. And after that, the gRPC proto compilers will take care of generating all the underneath serialization, or gRPC will do all the security underneath. As we talk further, it will do other features that this allows you to at one place do things like stats tracing, monitoring. When you need to get this in deployment, you can do all of those things, hook those things into gRPC library, and then your developers are just building their application logic, and they are getting the analytics is consistent, monitoring is consistent, you can hook in load balancing, and all kinds of good things can come to you. So that was my quick example. In a nutshell, we had an ideal to describe service API. We then we ran our proto compiler, generated the client stubs and server classes, extended those to create my service, and this example is present in across languages on our GitHub repo. So you just took the same example in case you need to again. And this takes, I'll go into more about HTTP2 feature set, etc. now. And the organization is at github.com gRPC. There is a sister organization also, github.com gRPC ecosystem. And I'll have more contact info, etc. So now I'm going to switch gear, as in, sure. So there is RPC library, etc. There are other ways of doing all communication between services, messaging between the services. So you need to know, what do I get by using gRPC? So I'm going to focus more now on what do you get when you use gRPC. So gRPC speaks your language. We have at Google for last 10 plus years have had development in 4 plus languages, and having a consistent development where each team can independently choose their language and still not worry about what the other team is developing has been a big benefit to us. We've extended that when we build gRPC. There are 12 plus languages today, increasing, and few more in implementation which are adding support for gRPC. Just a list of languages. The recent one has been Dart and Swift, Haskell, Rust. Those are being added, but most common languages are handled here. Just shows you that you can, in a company, you can have different teams using different languages and building their logic independent of each other and still communicating efficiently across each other. gRPC is ubiquitous. It's available on every platform, or we've been trying to expand it's built such that it can be available on any platform, and we've been expanding our platforms as these things go. And so if you think about it, it runs on Linux, Mac, Windows, your desktop operating systems, runs in your data centers, runs on your desktop, runs on your phone. We use mobile gRPC is used today in several Google applications, for example, and few other external applications to communicate with front ends or servers, Android, iOS, and it's being used by several embedded devices also, including routers, etc. So we do need help from the community here. Saying ubiquitous is not being ubiquitous. That's a goal, to be ubiquitous. And really, we as people working on gRPC don't have access to every different platform to test, try these things out, etc. So, and there are always new languages coming up. Kotlin came, people wanted to use Kotlin. So to create bindings for these new languages, newer environments, right, GraalVM, or more platforms. Somebody comes up with a new, one example of this was Alpine Linux. We didn't have support for it. So we need help on these things. Usually this just ends up making builds work and maybe fixing certain API calls that are going down to the system. And testing is very important, testing it on that platform. So if you're interested in contributing, we would love any help here. What does gRPC bring? It brings strongly typed service contracts. One of the problems in distributed systems, building distributed applications, is mismatch of assumptions between different components talking to each other. And it's very hard. Once you run into those problems, um, they can be obvious to a client doesn't talk to server. It's catastrophic, but you can debug it, or they can exhibit themselves in a very complicated way where your tail latency increases by a large amount of time because some assumption was not valid. So having strict APIs, strict service contracts is a great thing. gRPC along with protocol buffers gives you that. It gives you backward and forward conventions. So for example, if you don't reuse your tags, then you can always keep extending your service. We have services running which have been extended over 8 to 10 years at Google, and it successfully works. Yes, you do need to handle in your application logic. At some point of time, you do need to have conventions like semantic versioning and this thing, but it gives you a good mechanism to seamlessly give forward and backward compatible APIs. You can use your own conventions with gRPC. It doesn't enforce necessarily. So you can have RESTful services for many use cases. That's the right thing to do. You should build RESTful services. We also have conventions like just have one service per proto definition. At times, many people find it very convenient to have just one RPC per service. So you can have frame your policies and conventions around protos, and they make different policies and different conventions make sense. For example, if you wanted to build a CRUD system, you can always enforce that every service definition of an API has 4 methods. And then all your developers will build a CRUD-like system using gRPC. gRPC gives you performance and efficiency on wire. So gRPC is based on HTTP2, and HTTP2 has several benefits over HTTP. And this quick demo developed by HTTP2 demo guys just visually shows what type of performance benefits you get because of multiplexing and binary framing, etc. It has binary protos which are compact, so size on the wire is much smaller. And there are two people have been asked this question: hey, I can use a good compression mechanism and then reduce the wire, but yes, the compressing takes CPU cycle. So when you think of efficiency, you need to think of both. I need to create this representation efficiently, I want to get out of this representation efficiently, and I want to have smallest number of bytes. And we've been using protos. A lot of people have used protos, and people have seen amazing improvements. If you're using HTTP, JSON, or REST, you can see this blog post talks about 3x improvement in throughput, 11x improvement in CPU. So you can get lots of performance benefits through over, say, HTTP, JSON, REST using this. And then the libraries have been built, and performance is a key priority for us, and we've been building the libraries with performance in mind. So So next, gRPC libraries are built from ground up as a plugin framework. So they are very extensible, customizable. This is what we've learned, that different people have, so we've had multiple, different frameworks have different policies they want to enforce. So they need to intercept during the RPC flow. So we have interceptors. We have different transports. So we've built HTTP2 transport, but internally we have another bare metal transport that we are using building. You can build it on top of another file-based mechanism if you need to. Auth and security, one benefit of gRPC is it can encapsulate all the auth and security underneath. So we internally use LOAS and LOAS 2, and developers don't need to know. We can upgrade people, the whole Google just because they're using Stubby from LOAS 1 to LOAS 2 seamlessly. Not every application didn't need to make a change. That has been a big benefit. And there is a plugin auth mechanism. So we have mutual TLS and OAuth based authentication, and you can bring your, say Kerberos, you use Kerberos, you can bring in your auth mechanism and plug it in. Yes, you will have to do the work, but all the abstractions are built into the framework. Same for stats, tracing, monitoring. Several integrations exist. Prometheus, Zipkin, Open Sensors. Internally, we use Sensors, which is the equivalent of Open Sensors, Open Tracing, etc. You can use whatever you've been using. You don't have to change all of that infrastructure if you start using gRPC. All you have to do is hook it up through the clean extraction. Same for service discovery. And gRPC work with lots of supported proxies. Envoy has been a great partner. Nginx recently added support for gRPC. So you can use all these load balancing proxies, or whatever proxy you're using, you can use it with your gRPC applications. It's easy to use. As I demonstrated through example, hopefully it was clear that you think of your application logic and you build a distributed application without spending a lot of time upfront on worrying about networking and distributed systems. But a few other things. If you take gRPC libraries, they're super easy to install. We have published packages across languages. APIs are idiomatic. There are several concepts like errors. Errors are well standardized in gRPC, so, and they are propagated. So if you have a big graph of this you're talking through, it's very important that that error gets propagated to the client, because otherwise they don't know what happened. And so error propagation, reconnecting when there are any breakages of connections, cancellation propagation. So there's another concept, and Sree and Jan will cover in future talks these, but if you cancel RPC, you need to cancel it across all the graph it's going to traverse. So it's not just 2 points, the way I was talking. Effectively, when you have a complex scenario, you would have a complex graph through which your RPC will travel. And when you want to cancel, you want to propagate that cancellation. Same thing for deadlines. Every distributed call should have a deadline, because you don't know what's going to happen. And then if it's going to make subsequent calls, that RPC is going to create multiple graph of RPCs, you need to propagate that deadline with appropriate values. And these are some things which are, when you start writing, application get very complex, and having all these facilities makes it super easy to use and build applications using gRPC. Traditionally RPCs are thought as procedure calls or function calls, but gRPC extends it. Streaming is native to gRPC. Streaming is native to HTTP2 also. And so what that allows you to do is all the other use cases, you can frame your use case and use the type of RPC. If you just want to send some data and get some response back, you use unaries. If you're going to send lots of messages created over time, you use client streaming. If you want to get a bunch of updates from somebody, you use server streaming. And if you have a complex asynchronous chat-like application where two parties are going to send each other messages asynchronously, you use bi-direct streaming RPCs. Having all those concepts means that you don't have to build it on top of your networking protocol. Just the way I was showing you, you write your proto-IDL and you have a single RPC that you can keep listening on or sending messages using. It's open, standards compliant. It's been developed on GitHub. It's been in CNCF for over a year. We welcome all the contributions. We have a RFC-like process for discussing all changes that come up. And it's the wire protocol is well spec'd out based on HTTP2. It's a protocol defined on top of HTTP2 published. So having that makes the very easy to debug or understand, build tooling, or have ecosystem extendable. So when Nginx added their support for gRPC, they didn't have to even talk to us because we had developed the spec really well. And that really matters when as the ecosystem grows. And finally, it's a production-ready set of libraries, well-tested. We have large number of whenever for every change we are running large number of tests, continuous integration. We've been running fuzzing tests for almost 8 to 10 months now. The auto fuzzer developed at Google that has helped us find so many corner cases, because in communication, I/O, threading, race conditions, and those things are very common. All of those are taken care of for you by the RPC libraries, but for the same reason we need to worry about those internally a lot, because we need to know all the use case patterns by users. And we have had a lot of success with the fuzzing tests ourselves. gRPC has production debugging support or hooks for production debugging support based on what you use. Recently, we added a feature called Channel Z, which allows you to see on a service how many channels have been created to my service, what's the traffic on all of those, which are active, which are inactive, and all kinds of things. And it's been used in production by lots of companies outside Google and at Google, and so you can use it. So in a nutshell, I think I don't have to go over this. I covered most of this. So I'm going to open it up for question and answers, and I'm going to invite Sree, my colleague here, to join me for Q&A. He'll be covering the deep dive tomorrow. Thank you. And just I'll leave all the information for you in case you need to contact or you need contact information. Go ahead. Or I can repeat. I think the question was, do you still use Stubby at Google, or have you been using gRPC? We still use Stubby and we use gRPC both at Google. The migration is going to take us, if you think about it, as I was saying, there are, I can't give exact number, but multiples of tens of thousands of active binaries being built every day in Google. Moving all of these is going to take time. So right now we are in this hybrid scenario where we are using Stubby and gRPC both internally at Google. Go ahead.
You mentioned before that architects should take the time to design their API, and let's assume then someone evolving the API didn't take the time and didn't do their homework properly. Are there features in the protocol spec to evolve the API, like deprecate certain things and things like that to evolve it?
Yeah, so I think there is a two-phase answer to it. One is minor changes and evolving for minor changes, and second is major changes. What you want is you want to have flexibility of doing minor changes without really revamping completely the API. Otherwise, you're every 6 months revamping the API, and that's not one thing. For these minor changes, there are lots of facilities in this. As I was showing all those tag numbers in the protocol buffers, if you follow a simple convention that you never want to reuse a tag number, you can stop sending. You can have the field present in your proto. Don't remove it. Just add on new features. You don't have to populate it, and as it works fine for those type of changes. You do need semantic versioning. Typically, what we have found at Google is 3 to 5 years is a good time for a well-designed system. That's the time when you should need a semantic major version. Depending on how much time you can spend upfront, that your mileage may vary, but you can enforce semantic versioning through protobufs, through your server, saying that, hey, you know, this is my proto for V1 and V2, and then you have a server which you can have multiple servers or same server handling both services and protos.
Yes, my question is, since gRPC requires a schema, what is the recommended best practice for public APIs? How do a provider of the service publishes the schema. And maybe the second part of the question is, how does a consumer of the API deal with the essentially unknown version of the service, and how do you debug, serialization issues that result from it?
Sure. So to these things, for designing the system, we do require schema. That schema is also useful for building documentation, etc. If you wanted to build documentation, and we use gRPC for our cloud product client libraries, etc. And we have tools that generate documentation. Now I'll go into some minor details. gRPC as such, if not used with protocol buffers, is agnostic of schema. So the schema comes in when you use it in conjunction with protocol buffers. 2, gRPC also, most of the languages have this feature of reflection. So you can discover the service for methods if you want it from a client, if you didn't want to use predefined stubs that are created. So if you thought about it, there was a service class and server that gRPC created and the stubs created. A typical way of using would be stubs and creating documentation for your stubs. You should put lots of that's the best practice I would recommend. But if you don't want to use the stubs, or if you are building a proxy like application, etc., gRPC has a facility of reflecting, so you can find out what services it opens up. And Proto also has reflection, so you can find out what message types, etc., are there. You don't get all the benefits, but you get the flexibility. See? Okay. All right. Thank you, everybody.